In this screencast, I'm going to look at solving a second-order differential equation with some associated initial conditions. And the equation I've chosen to illustrate the method is d2y by dx squared minus 4y equals 2 cos squared x. Hopefully you remember that the total solution to this problem is composed of the sum of two separate solutions, the complementary function and the particular integral, which I'll denote by yc and yp respectively. And what we do is we find both yc and yp separately, and then we add the two together to give the final general solution. So to find yc, we note that yc is the solution to the associated homogeneous problem. So that is d2y by dx squared minus 4y equals 0. And what I do is I write down the associated auxiliary equation, which in this case is m squared for the d2y by dx squared term. Then there's no dy by dx term, so I have no m term. And then finally minus 4 for the 4y term. And that auxiliary equation is the result of substituting into the homogeneous equation the trial solution y equals e to the mx. And what I do is I solve for the auxiliary equation, and I get m equals plus or minus 2. Now, because those roots are real and distinct, I can say that the complementary function can take the form a e to the 2x plus b e to the minus 2x, where a and b are constants that we'll find later on. However, it's sometimes useful to write the complementary function in a different form when I have, as in this case, real roots that are equal but opposite in sign. So I've got plus or minus 2 in this case. What I can write instead is c sine 2x plus d cosh 2x, and if you think about the definitions of sine and cosh, hopefully you can see that those two statements are equivalent. And it just so happens in this case, with the given initial condition, that in fact this hyperbolic form is easier to apply the initial conditions to later on. So I'm going to take that form when I come to write out my final solution. So this is the complementary function, and what's very important is that you do not apply the initial conditions at this stage. Those conditions apply for y, the total y, not just the complementary function. So I have to wait until I've found the particular integral before I apply the initial conditions. So let's go on and find the particular integral now, and before I do that, let me just write out again for you the differential equation, because it's disappeared off the top of the screen. And what I'm going to do first of all actually is rewrite the right hand side of this equation using a trig identity. Cos squared of x is a half 1 plus cos 2x. So in fact the right hand side can be written as 1 plus cos 2x. And you'll see why I've done that in a moment. It makes finding the particular integral quite straightforward. So let me start to find that now, and what we have to do for the particular integral is make a guess as to what the solution should look like. Obviously an educated guess, and I look at the form of the right hand side of the differential equation. So I'm looking here at 1 plus cos 2x. First of all, with the 1, that's a constant term, so I'm going to guess a constant which I'll call p. And then I've got a cos 2x, and whenever you have a trig term, either a cos or a sine, you should guess both of the terms. So I'm going to guess q sine 2x plus r cos 2x. And what I now do is substitute this expression, this solution yp, into the differential equation, and I can equate coefficients and hopefully find the unknown p, q and r. So I'll do that now. First of all I need to differentiate yp twice. I'll do that all in one go. P is a constant, so it will disappear to 0. sine 2x, if I differentiate that twice, I get cos and then minus sine, so I get minus 4q sine 2x. And similarly, I get minus 4r cos 2x. So if I substitute those into the differential equation, which you can just see here at the top of the screen, I get minus 4q sine 2x minus 4r cos 2x. That's the d2y by dx squared bit. Then I get minus 4y and that equals the right-hand side, which is 1 plus cos 2x. And for this expression to hold for all r in the domain that I'm for all x in the domain that I'm interested in, what I need to do is equate coefficients. So I'm going to do that now, and first of all I'm just going to look at the constant terms. And if I look at the constant terms, you can see there's a p there being multiplied by minus 4, and there's a 1 there. Those must balance, so minus 4p equals 1, i.e. p is minus a quarter. If I now look at the cos 2x terms, I've got a cos 2x there, and a cos 2x there being multiplied by the minus 4 again, and I've got a cos 2x on the right-hand side. So what I get is minus 4r minus 4r again equals 1. So that tells me that minus 8r is 1, r is minus an eighth. And finally I look at the sine 2x terms. Minus 4q minus another 4q is 0, so q is 0. So in this case the particular integral is p, which is minus a quarter, then it was plus q sine 2x, but q is 0, so I don't have a term there, and then it's minus an eighth cos 2x, that's the r cos 2x term. You might like to have a think as to why it is in this case that q came out to be 0. If I scroll up, it's in fact up here because there's no first derivative in this expression. So in fact I would have been fine had I ignored q in the first place. I could have just had my particular integral as p plus r cos 2x. But it doesn't do any harm to put it in, and certainly had there been a first derivative there, I would have needed it in. So overall, what I get is, I'll just change back to blue, y equals the complementary function, which is c sine 2x plus d cos 2x, plus the particular integral, which is minus a quarter minus an eighth cos 2x. And that is what's called the general solution, because the constants that have come from integration have not been determined yet. But what I can now do is find them by applying the initial conditions. Now the first initial condition, it's disappeared, but I've got a note of it here. It's y of 0 equals 0. So if I put that into my solution, I get 0 equals c times sine of 0, which is 0, plus d cos of 0 is 1, minus a quarter, minus an eighth. So d in fact comes out to be 3/8. The second initial condition involved y prime, so I just need to differentiate first. I get 2c cos 2x plus 2d sine 2x, minus minus is a plus, a quarter sine 2x. And if I apply the initial condition, which was y prime naught equals 1, I get 1 is 2c, so that c is a half. And hence finally I can write down my solution, which is that y equals, and it was c, which is a half, sine 2x, plus d, which is 3/8, cosh 2x, minus a quarter, minus an eighth, cos 2x. And that is the particular solution to the original given differential equation.